Okay, this is really the best part probably of the year in many ways. This is where we get to take everything we've done and we get to do the main application of differential calculus, which is optimization. So look at a problem like this. A manufacturer wants to design an open box having a square base and a surface area of 108 square inches. So say that's, for whatever reason, that's the amount of material that they've calculated they want to use to make the box. What dimensions will produce a box with maximum volume? What do you think? Is this a problem you could do now? It honestly, given enough time, you probably could figure this one out, but without spending a lot of time on it. Is this one you can get the answer to? Anybody have a hunch what the box will look like? What do you think? If we want to, so we're trying to maximize the volume contained in this box. If it's got a square base, what do you think?
I think it's going to be on the smaller side.
On the, what do you mean the smaller side?
Like the box in total in terms of size, because when you get the bigger your box, the ratio to volume to surface area is smaller.
Okay, well that's interesting, right? So the volume, the ratio of surface area to volume is not constant. It's really not, right? Like it's, okay, this is an interesting topic. When you watch, if you watch some dorky movie where there are ants that are 8 stories tall, is that realistic? Or is King Kong realistic? No, it's not. I hate to spoil all these movies for you, but they're not. They're not realistic, because if you scale something up, like let's say you scale an ant up so it's enormous, it would never work. Anybody know why?
Legs wouldn't be able to support it.
Its legs wouldn't be able to support it. They wouldn't be able to support it. Well, why? Why wouldn't they be able to support it? I mean, you're just scaling everything up, so shouldn't the strength of the legs be scaled up in such a way that it would be fine? It's not. The volume of the ant, or sorry, the mass of the ant would increase proportional to what? As we scale an ant up, the mass of the ant would increase in direct proportion to what? The what?
The body.
Yeah, okay, but I want kind of I'm not looking for, I'm looking for just a geometric term here. You know, is it going to be the area? Is it going to be, what's going to scale with volume? Or with, I gave it away, with mass. It's volume, isn't it, right? The volume of the ant is going to correspond, is going to scale with the mass of the ant. So if we make the ant really large, like let's just say for argument's sake that the ant is this kind of a weird looking ant, it's sort of spherical, right? If we increase the dimensions of the ant by a factor of even just 10, you see that that's going to increase the volume by a factor of 10 cubed, right? If we made the ant, say, 10 times as tall, so the length dimensions are increasing by a factor of 10, that means the areas are increasing by a factor of 10 by 10, 10 squared, and the volumes are increasing by a factor of 10 cubed. So you're increasing the mass of the ant, even if you only make it 10 times bigger, you're making the mass 1,000 times bigger, but the cross-sectional area of the legs, if I cut through one of the legs and look at the area of the cross-section, that's what determines the strength of the legs. They're only increasing by a factor of 100. So do you see there that the mass is outpacing the strength in the legs by a factor of 10? And so at some point, the ant's just not designed, you know, it's to handle that extra mass. And so that would happen with anything. You just can't scale things up. It doesn't work. You couldn't make a building that was just scaled up so it was super enormous because the structure of the building couldn't support the weight. Okay. So yeah, so that's an interesting argument. Okay, that's not really what I'm looking for here, though. I'm looking for dimensions. What do you think? Is there a way? Do you think you could make a prediction about the dimensions of this box that's going to maximize volume? You don't even need to give me specific. I mean, does anybody have a hunch about how would the height compare to the width of the base, do you think? What's that? Really skinny and tall? I don't know. We'll find out. But what do you think? Taller than the base is? Okay. I'm just curious what your intuition is telling you about this. What do you think?
Could it possibly be really short with a large base?
Maybe. Yeah. What do you think? Any arguments for that stuff? I mean, it's just your intuition is not really well trained with this stuff yet. You haven't thought about it a lot. What do you think?
With a large base and a short height, it would have good support and a good base. And it would maximize our volume because we can extend the box outwards. But if we stayed short in height, it would make it so that way it was low to the ground in there. It was more, the surface area is more compact.
Okay, interesting. Okay, okay. Let me ask you this though: would you all agree that this is not a question that you really can answer right now? Right? You don't. You might have some hunches about what it's going to be, but we don't know. Right? The way we find out is, well, that's what optimization does for us. We really just get to use calculus, and look, we even have a table up here. We're going to use the same kind of calculus we've been using. Okay, how could we approach this here? Well, we're trying to maximize volume. So first of all, let's come up with a volume equation. So what is the volume of that box? And the dimensions are x by h. Yeah, it's x squared h, isn't it? Everybody agree? Okay. Okay, so there's volume. I'm going to want to find the maximum for volume, right? Okay. Any ideas about where we might go with this using calculus? Oh, okay, right. So if we were to graph volume, we want to find the place where the volume is the biggest on the domain that makes sense for us here. What's wrong with that function though? What makes this really two variables? Yeah. So what do we do when we have two variables? We've done some of this in the past with related rates.
Try to find in terms of age, or age in terms of x or something.
Yeah, right. We want a secondary equation then, right? So this is what we're going to call our primary equation, right? This is the optimization function. Whatever it is we're trying to optimize, which means minimize or maximize. In this case, we're maximizing something. We need to write a function for that quantity, right? That's going to be the output function that we're going to do calculus with. We want to find the absolute maximum for volume on the interval that we're going to define that corresponds to this problem. Okay, give me 1 to 5 on that. Does that make sense? Just kind of strategically where we're going with this, right? So we're going to have a table, and we want to find the absolute maximum using that table. Okay, we need a single variable though, right? So we need volume as a function of a single variable. So we've got to somehow be able to eliminate one of those variables, which means that our secondary equation has to be an equation that only involves h's and x's, right? Okay, well, the secondary equation, a lot of times, I like to call it an equation of constraint. And sometimes you hear that term. An equation of constraint makes sense because it's got to be some piece of information that constrains the problem. If I didn't give you any constraints here, I know immediately what I would do to maximize volume. I would make this box infinitely wide and infinitely tall. And it's kind of a stupid problem then, right? There's got to be some constraint on this that prevents me from just making it infinitely big. Well, what's the constraint in this problem?
Surface area.
Yeah, surface area, right there, right? We can see that the surface area is 108 square inches. Okay, so then we ought to be able to make some kind of equation of constraint, some secondary equation that uses that information. Okay, well, it's a surface area is what they gave us. What's the surface area of this box? Yeah, x squared, which is the area of the base, plus the 4 lateral sides of this thing, right? Each of them has an area of xh. Everybody agree with that? So x squared plus 4 times xh, okay? Okay, makes sense? Now we got to be smart about this. We want to be efficient. We want to be able to solve for one of those variables in terms of the other one. You get what I mean when I say that. I'm going to solve for one variable in terms of the other one means so the expression that we get only uses the other variable, right? And then substitute into the original equation. Which one of those variables would it be much easier to isolate and substitute? H. Everybody see that? How come? Yeah, it only shows up once, right? Good. The other x's show up in 2 separate terms. That would be really tough to do. So we want to solve for h. All right? So what is, if I solve for h, what do I get? Good. 108 minus x squared. I got to subtract that term to the other side and then divide by 4x, right? Everybody see that? Okay. Put a box around it. We always, since Algebra 2, we've always put, when we make a substitution, we put a box around the substitution equation. Okay. And then that's going in right there, right? Okay, look what that gives us. So that means that v now, as a function of x, is going to equal x squared times h. Right? So if I distribute the x squared, what do we get? Yeah, we could, right? If we distribute the x squared, we're going to get 108x squared over 4x. Well, 108 over 4 is what, 26? So I just get 26x when I make my first substitution, right? Minus x cubed over 4. Everybody agree? Okay. Does that make sense? Okay. So let's rewrite that. So that's our primary equation, or primary equation, or our primary function. There's our volume function as a function of a single variable, right? V of x equals 26x minus x cubed over 4. Okay, we need a domain for this thing too, though, don't we? If we're going to do calculus on this, we need to know the range of values of the input that makes sense. So x represents the width of the box, right? Okay, what's the bottom of my domain? 0, I guess, right? 0. Now, I want you to notice something. These variables are always going to compete. If they don't, so they're going to be inversely related, aren't they? If I've got a fixed surface area, as the width of the base goes up, doesn't that mean the height's going to have to go down because the surface area is constrained to be? Does that make sense? Okay, so x gets big, h gets small, and vice versa. Okay, so the question is then, could we actually have 0 for our width? Okay, yeah, why do we have to exclude 0 here? How come 0 doesn't work? Okay, so just kind of thinking of it conceptually, if the box were infinitely narrow, it would have to be infinitely tall, right? And we can't have infinities. We can't build something with infinities, right? So that's one way of thinking about it. So we can't include 0. Here's the other way of thinking about it. Remember what we said, as x gets small, h gets big, right? Okay, so look what happens. Let's go back down to the box. Let's look at the response of the variable h when we let x go to 0. If we let x go to 0, what is this telling us about h? See the problem? We're going to end up with a 0 in the denominator. We can't do that, right? Can't divide by 0, agreed? So 0 really can't be a part of our domain. Does that make sense? Okay. All right. What's the biggest this thing could get? How would we figure it out? Could we go up to infinity? Say it again. Well, I mean, that would mean approaching infinity, but there's a problem with that, right? Because I only have 108 square inches. So, I mean, how could the base be infinitely, right? There's going to be some place where we can't go and the base can't get any bigger, x can't get any bigger because we're constrained by the amount of material. Yeah, what do you think?
Wouldn't it be 108 for the square root of 108?
It's the square root of 108 is the answer, yeah. How can we see that mathematically? Well, here's a way we can do it. Because again, what's the smallest the height could get? I mean, at some point, wouldn't the height just go away and all of the surface area would just be the surface area of the base, which would have no volume, wouldn't really make any sense, agreed? But the height would go to 0 eventually if as the base gets bigger and bigger and bigger, right? So look at this equation right here. What's the value of x that's going to make the height go to 0? Yeah, look right there. Everybody see that? Look at this expression on the top. Height equals 0 when x equals the square root of 108, right? Does that make sense? See where that's coming from? Okay, that's a really good trick on these things. When you're trying to figure out what the domain is always look at, both of the variables, because as one goes up, one goes down, right? And you can kind of look at that at the secondary equation, and a lot of times that'll give you that's the easiest place to see, what the boundaries on the domain are going to be. Okay, so then our upper limit would just be the square root of 108, and look, our table is on its way. Okay, and we do include the square root of 108. It's not a very good box for us. It has 0 volume, but I mean, we'll include it. It doesn't violate reality, at least, right? Okay, make sense? Well, what are we going to do? Here's our table. Instead of f of x, we have v. So what are we going to do with all this stuff? Yeah, we're just going to do calculus. Now we flip into calculus mode. And what you'll find is, the good news is when you're doing optimization problems, almost always the calculus is going to be a piece of cake. Like, these are not really difficult. Like, you dealt with some pretty tough functions with curve sketching. With these, usually they're going to be really simple equations, right? Really simple functions to differentiate. Okay, so let's do the calculus. Let's get that down a little bit. Oh, I want to do that. That's probably enough room right there. Okay, so let's look at we got to differentiate now, right? What's our derivative? Okay. Agreed? Okay, so we can, when's that 0? Yeah, what would that be when x squared equals 4/3 times 26? Right? So what's that going to be? It's when x squared equals, what's that going to be? 108 divided, square root of 108 divided by 3. Or 108 over 3. Did I do that right? I think so. Right? So x would just be plus or, actually, plus or minus? Do I need the minus? No, I only need the positive one, right? Because that's the only value that's in my domain. Okay? What's that? Did I mess that up?
Where did you get the 108?
Oh, is it 10? It's 104, isn't it? Yeah, sorry. Right? So is that?
Yeah. I don't know, I need my paper on my.
Yeah, so that actually got messed up a little bit, didn't it? What's 108 divided by 4?
I don't know.
27, not 26, right? Okay, so then we got to change a couple things. So then this should have been, that's going to change a few things. Let's see here. We got, that should be a 27. That should be a 27. And so now that does give us 108, right? That makes sense? Okay, so now if we did,
It's a square root.
you just square root it, yeah. And we don't even really need to, we just need a decimal approximation is fine, right? Because we just want to get like a number that we could measure.
108 divided by 3 is 36, right? So I just square root of 36.
So it's, hey, it's 6, what do you know? Yeah. How'd I get what? How'd I get the yellow? I just set, yeah, I just set it equal to 0. So just when 3/4 x squared equals 27, right? Then I just multiplied by 4 and divided by 3. Yeah. Okay. Okay, so yeah, so we get, that's convenient. It works out to be 6. Our only critical number is at 6, which is a 0 of the first derivative. And we get to decide here if we even want to do a second derivative, right? Because it's not specifically asking us for concavity.
So that would have to be a maximum then, say?
Well, what's your reasoning?
Well, it's the only critical number.
Yeah, it's the only critical number. And if the volume is approaching 0, it's 0 at one endpoint and it approaches 0 at the other endpoint, right? So that's a good way of thinking about it. Yeah, it is. We could show it pretty easily. Would we want to take a second derivative here? Yeah, we would. Because look, it's a polynomial. It's so easy.
So then, and then you don't have to do any test.
Right, right. And then, see what I'm saying? We can easily do a second derivative. That goes away. What's the second derivative? Yeah, negative 3/2 x. For any positive value of x, the second derivative has what sign? In our domain, it's always negative, isn't it? Right? Negative 3/2 times whatever our input is always going to be negative. So in our table, we can see right here in our table then, we know what this is going to be. It's a relative maximum. And if we've got this function that's, it's a polynomial, right? So it's smooth, it's continuous and differentiable everywhere, right? Smooth function. If it's only got one internal critical number, then it's a maximum. That has to be the absolute maximum. We don't have to check endpoints, right? Make sense? So we got it. Look at that. We figured it out. So x equals 6 maximizes volume. If I want to find the height, I just plug 6 in there. So 108, what does that give us? 108 minus 36 is 72 over 24, so 3 for the height, right? That's it. Those are the best dimensions we could use, would be 6 by 6 by 3. That's the box that gives us the most volume for the most bang for the buck there. Did anybody think it was going to be cubic shaped? Did that kind of make sense? What would have made the answer a cube?
If it all had to be like the same size. It said the base had to be square, so if all sides had to be square.
Well, that would make it a cube. But if we change this problem slightly, our answer would have been, we would have had the same. All 3 dimensions would have been the same if we had done what? Anybody know?
If the constraints of curvature?
Well, no, it wouldn't matter. The surface, we could pick we could have picked the surface area to be any number, and the proportions would have been the same. The height would have always been half as big as the width of the base. If it had a lid. If it had a lid, this would have been a cube. Anybody?
It would be.
Like a sick face. Like you lit on a cookie jar that y'all can.
That would have changed things, right? And then it's, I mean, we could let's show that. It's super easy to show.
2x squared, instead of x squared?
Yeah. So let's just show that. The volume would have been, in that case, the volume would have been the same thing, right? It would have been x squared times h. We don't know what h is yet, right?
Surface area would be 2x squared.
Surface area would have been,
2x squared.
yeah, it would have been 2x squared. Right, and if we set that equal to, what would be a better, let's pick a better surface area. Let's say, let's pick 216, how about? So just, we'll just pick a little different, we'll just pick a little different value. What's that?
6.
Oh yeah, what do you know? Yeah. Let's just say, but again, I'm just picking that so we get whole number dimensions. It could be anything. It's not going to change the proportions of the side lengths. So if we did this and we solved this thing, well, now we could divide this by 2, right? And we get x squared plus 2xh equals 108. And so if we solve for h equals 108 minus x squared over 2x, that would be our new substitution equation. If we plug that in, v would equal x squared times that. We could just cancel one of those. And so we're going to get 108, actually what, 54x minus x cubed over 2. Everybody agree? Okay, if I differentiate this, v dot equals 54 minus 3/2 x squared. If I solve for x, what am I going to get? What's that? I mean, I could have, but why not just, why I canceled one? Just because if I, oh, I could have, but you mean just use that equation?
Instead of that, do 6x squared. Because you have to take into account the height. The height's not x.
We don't know for sure that the height is equal to x.
Oh,
If it's a
Well, but we're proving that. Yeah, we're doing the same problem where we don't know we're saying that the base has to be square. If we have a lid on it, we're going to determine the height, that, you know what I mean, the dimensions. And so then if we solve this, this would just give us, it messed up. So that would give us, I promise you, that's going to give us x squared equals 36. 2/3 of 54 is 36. So x equals 6. Well, what do you know? If I plug 6 in to the height equation, I'm going to get back 72 divided by, I'm going to get 30, height equals 6, right? I'm going to get 72 over 12, which is 6. Okay? And so it worked out in that case that the height is equal to 6 also, and so we did get a cube. Okay? I mean, we didn't really need to do that one. That's not the original question. So then what are the steps we go through? So here's kind of your recipe, and I'll print this out and give it to you, and I'll put this in the handouts. But our recipe for optimization problems, then we kind of break it down to something like this. This will look similar to what we did for related rates problems. We want to assign symbols to all the variables, so x's and y's and r's and things like that. When we can make a sketch, make a sketch. That's very helpful. And then our goal here is to write a primary function that for the quantity that's going to be maximized. Okay? If the primary function only has one independent variable, we're good. We just do calculus. If it doesn't, then that means we have to come up with a secondary equation and make a substitution so we can turn this into a function of a single variable, right? And if that's the case, the secondary equation is always going to come from the constraint, whatever's constraining this to be non-infinite or non-zero if we're trying to minimize something, right? That's going to be where we're going to get that secondary equation. Then we're going to plug that back in, turn this into a primary function of a single variable. We have to determine the domain that's going to work, and that's really important because we only are going to look for critical numbers in our domain. And then we just use your skills and make a table and figure it out, right? And then go back and interpret the solution to your calculus table within the context of the problem, and we're done. That's it. Yeah, that's right. Okay. So we're not going to be able to do this today, but how could we start to think about this one? We have to rephrase this in a way, or think of it in a way where we could come up with some function to maximize or minimize. What could that function be that I'm trying to maximize or minimize here? What's that? Well, we're not to that point yet. I just want to know what's the primary function going to be, though? What's the thing the quantity that we're trying to minimize or maximize in this problem? No. In the last one, it was volume that we were maximizing. The question doesn't specifically ask you to maximize or minimize something, but you got to figure out what it is. You have to turn this into a problem that uses the word maximize or minimize, at least in your head. What would it be? Yeah, right? We want to minimize the distance between some point on the graph of this function and the point 0, 2. Does that make sense? Now that's something we can sink our teeth into. Now we know that we're trying to minimize a distance. We just have to now focus on coming up with a function for distance, right, that's going to work for us here. That's going to be a function of probably what variable? I mean, maybe, but probably x, right? Does that make sense? Okay. Think about the distance formula. Like we could draw a picture even with this. When are we out of here? 45. Okay, so we could maybe at least draw a picture on this one. Then we'll come back on Monday and talk a little more about this. Okay, so here's our picture, right? Let's take a look. So what does the graph of 4 minus x squared look like? That's a pretty easy one. Yeah. 4 minus x squared is an upside down parabola with a vertex where? 4, okay. X-intercepts where? Yeah, -2 and +2, good. So it's just going to look kind of like that, right? And we're trying to minimize the distance between the parabola, a point on the parabola, and the point 0, 2. Right? Everybody agree? So let's just pick some random point here. Here's some random point on our curve that has coordinates, what? X, Y. Yeah, it's variable, isn't it? Right? Okay, so then this is really the triangle we're looking at is just this little triangle maybe right there. Let's magnify that. Oops. So it's a right triangle. Isn't the base of that is just x, right? Everybody agree? The hypotenuse is what we could call d for distance, how about, right? And the height, isn't that, well, that's 2 and that's y, so isn't it just y minus 2? Everybody agree?
Yeah.
Everybody buy that?
Yeah.
Because if that y coordinate is y and that y coordinate is 2, then the difference in those would be the height of that little triangle, right? Okay, well then that's just a Pythagorean relationship, right? D squared equals x squared plus the quantity y minus 2 squared, right? Everybody agree? D is the quantity that we're trying to minimize. What's going to be wrong with our equation, though? We don't have x or y, but the problem, I mean, it's okay to have a variable, but if this is somehow going to be our output, let's say, and really, let me ask you this, do we need to solve, does it ever ask for what the distance is? No. We just want to minimize the distance, right? Well, wouldn't the minimum value of distance also be the minimum of d squared? Wouldn't it? Right? If we find the smallest value for the distance d, wouldn't that also be the smallest value for the square of d? Everybody get that? So how about if we do this? How about if we just call it capital D and it's actually equal to distance squared? But that's okay. Let's just minimize that quantity because it's a lot easier to work with. I don't have to introduce a radical. Everybody get that? Kind of a good trick. So now we have d equals x squared plus the quantity y minus 2 squared. D is the quantity we're trying to minimize. What's wrong with our function, though? How many variables do we have? Well, I mean, we have how many input variables? That's a problem, right? What's our equation of constraint going to be? They gave it to us. What constrains this particle not just to be infinitely close to 0, 2? Let's just make the x and y coordinates 0, 2, and it's right there. But I can't because of that. It has to sit on that function, right? So here's the constraint. It can't be on that point because that point's not a solution of that equation, right? See what I'm saying? Okay, we'll talk on Monday. Do you? I bet you're starting to, though.
I understood the first one.
Good.